question is, the driving point impedance of the network shown in the figure is given by Z of S equals to S plus 3 by 2S square plus 6S plus 1. The values of the components are, see, the impedance function for the network can be written as Y of S equals to CS plus 1 by R plus SL. So whatever the function we have, that is Z of S equals to S plus 3 divided by 2S square plus 6S plus 1. So we can convert Z of S into Y of S, that is 1 by 2S square plus 6S plus 1 by S plus 3. So equals to 1 by Y of S. If we compare this one, Y of S equals to 2S square plus 6S plus 1 divided by S plus 3. So we can write this as 2S by S plus 3. So we can write this equation as like this. So 2S square plus 6S plus 1 divided by S plus 3 is going to be satisfied. So if we compare this equation 2 with equation 1, we will get C as 2 farads, L as 1 Henry, R as 3 ohms, which is the option A is correct. The H21 parameter of the two-port network shown in the figure. See, the equation for the calculation of H21 is equals to I2 by I1 and making V2 equals to 0. That means 10 ohms 2I2, this is I1, this is plus V1, 20 ohms I2, we have to make output short circuited. This node I am taking as VA. So if we apply the KCL at node VA, we will get minus I1 plus VA by 10 plus 2I2 minus I2 equals to 0. VA equals to minus 20 I2. If we substitute this equation into this, we will get H21, that is I2 by I1 equals to minus 1, which is option B is correct. Find the initial value of X of S. Here we know from the initial value theorem, that is limit t tends to 0 x of t equals to limit s tends to infinite s into x of s. If we substitute this one, that is s into 2s plus 6 by s into 4s plus 2. So as s tends to infinity, the s term is going to be significant, so it is going to be 2 by 4, which is equals to 0.5. Hence option B is correct.
A power diode has rate of fall of the diode current as 20 amperes per microseconds. Okay, he has given as di by dt is equal to 20 amperes per microseconds, and the storage charge Q is equal to 50 microcoulomb. Now what is the peak reverse current? Peak reverse current IRR is given as 2k into square root of di by dt. So this is 2 into 50 micro into 20 by 20 ampere per microseconds. Okay, this is under root. Now what is the answer is that square root of 40 into 2 into 50. So this is 63.24 amperes.
This Nyquist plot will give the. Here we know two relatively means in order to calculate the stability of a system from a Nyquist plot, we will take two parameters for the measurement of the stability. Those two parameters are gain margin and the phase margin. We know these two parameters are relative stability measurement parameters. because gain margin is nothing but calculated with respect to phase crossover frequency, phase margin calculated with respect to gain crossover frequency, where a gain becomes 1. Here the phase crossover frequency is the frequency where the phase becomes minus 180 degrees, means this gives the relative stability with respect to minus 180 degrees, and phase margin will give the with respect to unit magnitude. So it gives the relative stability, which is option D is correct. Is in lead compensation, the 0 is here. If we go for the explanation, see, if we calculate the transfer function, suppose y of s by x of s of lead compensator, we can write it as beta ts by 1 plus alpha ts, suppose. So the angle criteria of the transfer function is equals to tan inverse of beta t omega minus tan inverse of alpha t omega. For the lead compensation, the angle must be greater than 0. Then only we can say that this is providing a lead compensation. So for that one, tan inverse of beta t omega greater than tan inverse of alpha t omega. So beta t omega greater than alpha t omega. So beta should be greater than alpha, means we know that here the 0 is 1 by beta t, whereas pole is at 1 by alpha t. Here beta is greater than alpha, hence 0 occurs. Near to the origin compared to the pole. Hence, option A is correct.
Okay. In this question, the maximum internal power dissipation allowed for SCR, which can withstand a temperature, that is junction temperature of 90 degrees. He has given Tj as 90 degrees centigrade and having ambient temperature, let us take it as TA. TA is of 55 degrees centigrade, and thermal resistance is represented with theta JC between junction to ambient, that is JA, which is equal to 2.5 degrees centigrade per watt. Now we have to calculate maximum internal power dissipation. Okay, now maximum internal power dissipation, let us take PAV is equal to, PAV max is equal to Tj minus Ta by theta Ja. Okay, this is the formula for maximum internal power dissipation. We have 4 temperatures: junction, sink, okay, junction, sink, ambient, and one more is case. Okay, internal power dissipation P average maximum Tj minus Ta by theta Ja, which is 90 minus 55 by 2.5. So this one is, what is the answer here? Answer is B, that is 14 watts.
How far does the memory of the moving average system described by the input-output relation y of n extend into the past? Suppose, see, y of 0 equals to 1 by 3 x of 0 plus 1 by 3 x of minus 2 plus 1 by 3 x of minus 4. Similarly, y of 4 equals to 1 by 3 x of 4 plus 1 by 3 x of 2 plus 1 by 3 x of 0. That means the output at 4th instant not only depends upon the input at that particular instant, but also it requires x of 0 sample, means 4 samples beyond that one. Hence it requires 4 times memory of the past samples. Hence option D is correct.